Ever heard the saying, the stone the builders rejected has become the cornerstone? Well, that is the exact situation with this newly advanced Israeli aircraft. Developed for the United States Air Force, this aircraft received several criticisms and was eventually rejected. However, Israel found a purpose for it, and the result turned out to be quite mind-blowing. This aircraft was redesigned in such a way that made it totally unrecognizable, boasting advanced features that makes it a beast in the skies, effortlessly dominating. Even the United States is shocked at the outcome of this new aircraft that they once rejected. Why was this airfighter rejected by the United States? How did this airfighter get totally transformed? Join us as we explore the intriguing features of the new advanced Israel aircraft that the United States and Russia could not help but be stunned about. If the United States ever rejected an aircraft, it is probably because it did not serve its purpose and didn't live up to expectation, or there was a better option. But instead of assuming, let's take a dive into the interesting history of the YF-23, why it got rejected by this nation that prioritizes advanced technology, what aircraft it lost to, and how it got transformed into the Mitsubishi F2. In 1978, American satellites first spotted the advanced Soviet Su-27 and MiG-29 fighter prototypes, which worried the U.S. because it smelled like trouble. These new Soviet models were expected to match the maneuverability of United States fighter aircraft. Additionally, new Soviet systems like the A-50 airborne warning and control system and advanced surface-to-air missiles posed further threats to U.S. air power. 3 years after these aircraft by the Soviet were spotted, the United States Air Force began developing requirements and discussing with the aerospace industry concepts for an advanced tactical fighter that would replace the F-15 Eagle. This new fighter would use emerging technologies like composite materials, lightweight alloys, advanced flight control systems, more powerful engines, and stealth technology. The United States Air Force released an ATF request for information in May that same year to several aerospace companies to get ideas for the new fighter. Initially called Senior Sky, the ATF's requirements were still being defined, leading to various responses from the industry. Northrop submitted 3 designs ranging from very low cost to highly agile and low observable missile carriers, all being small and light. In 1983, the ATF System Program Office was formed at Wright-Patterson Air Force Base. After discussions, the SPO made air-to-air combat with excellent kinematic performance the main role for the ATF, which would replace the F-15 Eagle. Northrop's response was a Mach 2+ fighter design called N360 with delta wings, a single vertical tail, and twin engines with thrust vectoring nozzles and thrust reversers. Around this time, the SPO began to emphasize stealth due to successful results from the Air Force's secret projects like the HAV Blue F-117, Tacit Blue, and the Advanced Technology Bomber Program, which resulted in the B-2. Northrop also quickly adapted to the ATF's increasing focus on the stealth feature. Since October 1981, a small team of engineers under Rob Sandusky within its ATB/B-2 division had been working on stealth fighter designs. Sandusky became the Northrop ATF's chief engineer, and fellow B-2 stealth engineer Yuping Liu joined as the chief scientist in 1985. They studied 3 design concepts: the agile maneuverable fighter similar to N360 with 2 canted vertical tails and great aerodynamic performance but minimal stealth; the ultra-stealth fighter emphasizing maximum stealth with only 4 radar cross-section lobes and nicknamed Christmas Tree for its shape; and the high-stealth fighter balancing stealth and maneuverability with diamond wings, all moving V-tail rudder vaders, engine exhaust troughs, and aligned edges. The HSF, taking cues from the B-2 to reduce radar and infrared detection, evolved to resemble the eventual YF-23, balancing stealth and aerodynamic performance. By November 1984, the concept exploration phase had allowed the ATF System Program Office to refine its requirements and release the Statement of Operational Need. This document called for a 50,000-pound fighter with stealth capabilities and excellent kinematics, including prolonged supersonic flight without afterburners, known as supercruise. A year after, the USAF issued a request for proposal for the demonstration and validation phase to several aircraft manufacturers. The top 4 proposals would move forward, later narrowed down to 2. Along with technical requirements, the RFP emphasized systems engineering, technology development plans, and risk mitigation. After discussions with Lockheed and Northrop about their stealth experience with the F-117 and B-2, stealth requirements were significantly increased. The requirement to evaluate prototype air vehicles from the 2 finalists was added in May 1986 following recommendations from the Packard Commission. At this time, the USAF planned to procure 750 ATFs at a unit cost of $35 million in 1985 dollars. The United States Navy also planned to use a version of the ATF to replace its F-14 Tomcat, calling for the procurement of 546 aircraft. Northrop's work on the high stealth fighter paid off for the DEM-VAL RFP. By January 1986, HSF evolved into Design Proposal 86E, a refined and well-understood concept through extensive testing. This company's experience in designing stealthy curved surfaces, gained from projects like Tacit Blue and the B-2, gave them an early advantage. Lockheed, on the other hand, having relied on faceted designs like the F-117, had to develop new methods with curved, stealthy surfaces. Northrop's HSF design was further refined into DP-110, their submission for the DEM-VAL RFP. After a long development window, the proposals for DEM-VAL were submitted by Lockheed, Boeing, General Dynamics, McDonnell Douglas, Northrop, Grumman, and Rockwell. Grumman and Rockwell soon dropped out because they couldn't keep up. Moving forward, companies were expected to invest significantly in technology development, so teaming between companies was encouraged. Lockheed, Boeing, and General Dynamics formed a team, as did Northrop and McDonnell Douglas. On October 31, 1986, Lockheed and Northrop, the 2 leaders in stealth aircraft, were selected as finalists for DEM-VAL, with Lockheed in first place and Northrop in second. Despite Northrop's refined design, Lockheed's focus on systems engineering gave it an edge over the other competition. Both teams received $691 million and had 50 months to build and flight test their prototypes. Pratt & Whitney and General Electric were also contracted to develop the engines for the ATF competition. Due to political pressure, the prototype air vehicles were not meant to perform a competitive fly-off or represent a production aircraft meeting every requirement, but to demonstrate the viability of the concept and mitigate risk. Northrop, one of the winning companies for the DEM-VAL proposals, led the YF-23 team with McDonnell Douglas, who they had worked with before on the F/A-18 Hornet. Together and as a team, they invested $650 million into the ATF effort. Northrop built the rear fuselage and tail in California and did the final assembly at Edwards Air Force Base, while McDonnell Douglas built the wings and front fuselage in Missouri. It's important to note that the YF-23 design mainly came from Northrop's DP-110, with very little input from McDonnell Douglas's less stealthy design. However, their prototype evolved into DP-117K in January 1988, featuring a sharper nose for better radar performance and a strengthened rear deck. The aircraft was built with its large composite skin structures, first before the internal parts. Northrop developed the flight control laws using a simulator and a modified C-131 aircraft called the Total In-Flight Simulator. Throughout the DEM-VAL phase, the SPO reviewed performance and cost studies with both teams and adjusted requirements as needed. Initially, the ATF had to land and stop within 2,000 feet, requiring thrust reversers. However, this requirement changed to 3,000 feet, and by 1988, thrust reversers were no longer needed, allowing for smaller engine housings. Also, the number of internal missiles was reduced from 8 to 6, and it came with a struggle. Both teams struggled to meet the 50,000-pound takeoff weight goal, so it was increased to 60,000 pounds, and engine thrust was increased from 30,000 to 35,000 pounds. But that's not all. The ATF also needed advances in avionics and sensor systems for better situational awareness and to reduce pilot workload. The YF-23 was a demonstrator for the airframe and engines, so it did not include mission systems avionics. Northrop and McDonnell Douglas tested these systems separately, with Northrop using a modified BAC-111 aircraft, and McDonnell Douglas building the avionics ground prototype. Avionics requirements were also adjusted during DEM-VAL, with the infrared search and track sensor being made optional in 1989. The first YF-23, which was painted charcoal gray and nicknamed Gray Ghost, was rolled out on June 22, 1990, and had its maiden flight on August 27, piloted by Alfred Paul Metz. The second aircraft, painted in 2 shades of gray and nicknamed Spider, flew for the first time on October 26 with Jim Sandberg as the pilot. The first prototype briefly had a red hourglass painted on its ram air scoop, resembling the Black Widow Spider's marking, which led to the unofficial nickname Black Widow II. However, Northrop management had the marking removed when they found out about it. A proposed naval version of the YF-23, sometimes called the NATF-23, though it never got an official name, was considered as a replacement for the F-14 Tomcat. However, the initial YF-23 design was inspected but had problems with flight deck space, handling, storage, landing, and catapult launching, which required a different design. The design was later narrowed down to 2 configurations, DP-533 with 4 tails and DP-527 with 2 tails and canards. The latter was eventually chosen as the best option. The NATF-23 design was submitted along with the F-23 proposal for further development in December 1990. But by late 1990, the Navy started to back out of the NATF program and fully abandoned it by FY 1992 due to rising costs. A wind tunnel test model of DP-527, tested for 14,000 hours, was donated by Boeing St. Louis in 2001 to the Bellefontaine Neighbors Klein Park Veterans Memorial in St. Louis, Missouri, but with the canards removed. The YF-23A was a prototype designed by Northrop to meet USAF requirements for survivability, supercruise, stealth, and easy maintenance. It had a unique look with diamond-shaped wings, an aerodynamic profile to reduce drag, and all-moving V-tails. The cockpit was positioned high near the nose for good visibility. It had tricycle landing gear, with 1 leg at the nose and 2 main legs. There was a large weapons bay underneath the fuselage between the nose and main landing gear. The cockpit featured a center stick and side throttle. Also, it was powered by 2 turbofan engines in separate nacelles, with S-ducts to shield them from radar. The inlets were trapezoidal with panels to manage airflow. The first prototype used Pratt & Whitney YF-119 engines, while the second, PAV-2, had General Electric YF-120 engines. It had single expansion ramp nozzles and, unlike the YF-22, did not use thrust vectoring. The exhaust flowed through tile-lined channels to dissipate heat and avoid infrared detection. The YF-23 could supercruise at over Mach 1.6 without afterburners. The aircraft had relaxed stability and was controlled by a fly-by-wire system managed by a central computer. It used its wing flaps and ailerons for roll, and the V-tail fins for pitch and yaw control. Test pilot Paul Metz noted that the YF-23 had an excellent high angle of attack performance, up to 60 degrees. For aerodynamic braking, the wing flaps were deflected down and ailerons up simultaneously. To save on prototyping costs, commercial parts were used, including an F-15 nose wheel, F/A-18 landing gear parts, and forward cockpit components from the F-15E Strike Eagle. The planned production version of the F-23 would have been different from the YF-23 prototypes in several ways. Instead of a single weapons bay, it would have had 2 tandem bays in the extended forward fuselage, one for short-range AIM-9 missiles and another for AIM-120 missiles and bombs. An M61 rotary cannon would be installed on the left side of the forward fuselage. The overall length would be slightly increased to 70 feet 5 inches, while the wingspan would stay about the same. The fuselage would be bigger, with a larger nose to fit mission systems, including an AESA radar. The forebody Chinese would be less pronounced and raised to the same height as the leading edge of the wing. Removing the thrust reversers allowed the engine nacelles to be smaller and more rounded, with the space between them filled in to maintain aerodynamic smoothness. The inlet design would change to a serrated semicircular shape with a compression bump. The fuselage and empennage trailing edges would have fewer serrations, and the engine thrust lines would be angled inward by 1.5 degrees. The production proposal included both single-seat F-23A and two-seat F-23B variants. The naval variant, NATF-23, had many changes to meet aircraft carrier operation requirements and a greater focus on long-range sensors, weapons, and loiter time for fleet air defense. The diamond wings were positioned as far back as possible, and the aircraft had ruddervators with more serrations to reduce length, folding wing capability for storage, reinforced landing gear, a tailhook, and slightly canted canards for better maneuverability at low speeds for landing on carriers. It also had thrust vectoring nozzles. Its inlet design was a quarter circle with serrations and a compression surface. The internal weapons bay was divided into two compartments by a bulkhead for added strength and could accommodate AIM-152 advanced air-to-air missiles, as well as possibly AGM-88 HARM and AGM-84 Harpoon missiles. Its bay doors would carry AIM-9 missiles, and an M61 rotary cannon would be in the right wing. It also had a wingspan of 48 feet, a length of 62 feet 8.5 inches, and a folded wingspan of 23 feet 4 inches. Like the Air Force version, the NATF-23 had both single-seat and two-seat variants. Today, the two YF-23 prototypes are displayed in museums. This sums up the reasons why YF-22 was selected as the winner. Not because the YF-23 prototype was terrible, far from it. The Northrop prototype simply did not meet the standards of the YF-22, now known as the renowned Raptor. Now let's focus on the YF-22 and its transformation into the Mitsubishi F-3. In October 2020, Mitsubishi won the right to develop a new fighter jet. Instead of starting from scratch, they decided to buy and update an old project from another country. This project was the YF-23, which they used to create Japan's latest fighter jet, the Mitsubishi F-3. The F-3 is a sixth-generation fighter jet designed for air superiority, incorporating advanced technologies like combat lasers and electromagnetic weapons. This makes it a formidable opponent. It has two powerful XF 9-to-1 engines with afterburner thrust of 16,500 kilogram force each, double that of the American F-35. They are also considering engines with variable thrust vectoring for better maneuverability. A key feature is its ability to generate 180 kilowatts of electricity, which could power combat lasers or electromagnetic weapons to disable enemy electronics from up to 9 miles away. The F-3 also has 6 points to carry traditional weapons, such as guided hypersonic or nuclear missiles. This sixth-generation aircraft boasts advanced onboard equipment, including a sophisticated interface to streamline piloting and combat, and a body that doubles as a radar antenna and electronic jammer. It has a rapid system for processing and transmitting data from all its surveillance and guidance systems, from ground radars to airborne gunners. Japan not only revived the YF-23, but also transformed it into a technologically advanced sixth-generation fighter. Meanwhile, the United States is focused on developing a new, unique aircraft, the SR-72. In December 2014, NASA gave Lockheed Martin a contract to figure out if they could use current turbine engine technology to make the SR-72's propulsion system. The contract, worth almost $1.13 million in today's money, pays for a study to see if they can mix a regular turbine engine with a special ramjet engine that works at very low speeds. NASA had already funded a study by Lockheed Martin that showed they could reach speeds up to Mach 7 with an engine that can switch between turbine and ramjet modes. The challenge with superfast engines has always been the gap between how fast a regular jet engine can go and how fast a superfast engine like a scramjet needs to go. The study is looking into making a turbine engine that can go even faster or a scramjet that can work at slower speeds like a regular jet engine. Like the predecessor, the SR-71 Blackbird, the SR-72, also known as Son of Blackbird, will dominate the skies with no loss recorded because it is a better version and is equipped with a more advanced technology, making it more than capable of taking on present-day threat without breaking a sweat. Also, this aircraft incorporates the capabilities of its predecessors in advanced AI, making it extremely powerful. It is designed to be invisible to radar and can handle entire armies while staying unharmed. Its secret lies in its speed, reaching over 4,350 miles per hour. The SR-72's speed and low visibility make it incredibly dangerous. But that's not all. Recently, the Pentagon revealed a secret electric silent fighter jet called the X-65 that was developed by DARPA. This secret aircraft abandons traditional control surfaces in favor of active compressed airflow control, allowing for ultra-fast maneuvers. It also uses a quieter and more efficient electric motor, enabling it to approach enemies undetected and significantly increasing its range. The sole purpose of developing this secret aircraft is to demonstrate the feasibility of active flow control. AFC utilizes bursts of air rather than moving flight control surfaces on the exterior of the wings and tail to control its flight. Let's not forget the NGAD program that is set to take the world by storm. The United States is ready to dominate and is leaving no stone unturned to achieve this. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.